Welcome back to another video. Today we are going to the new topic, which is Euclidean algorithm. So the ancient mathematicians Euclid create an efficient method to calculate the greatest common divisor of two integers, and this method is called Euclidean algorithm or Euclid's algorithm. With this algorithm, you can compute the greatest common divisor of A and B. And you can find integers x and y such that the greatest common divisor of A and B equal ax plus by. Now, take a look at the statement of Euclidean algorithm. So if you want to calculate the greatest common divisor of A and B, you need to let A and B be integers and let A to be greater than 0. So in this case, A is the divisor. Okay? And then to use Euclidean algorithm, there must be integers q1, q2, q3 all the way to qn plus 1, and then r1, r2, r3 all the way to r1. So these are integers satisfying these equations. Now, for the first one, what do we have right here? We're going to have b equal aq1 plus r1. These equations means that we divide b by a, and we have the quotient of q1, and the remainder is r1. So that the remainder is greater than 0 and less than a. And once the remainder is less than the divisor, we divide a by r1. So we're going to have a equal to r1 multiplying the quotient plus r2, where r2 is the remainder greater than 0 and less than divisor. So that we have these equations. Once we have r2 less than r1, we divide r1 by r2. So we're going to have this equation. So we're going to have r1 equal r2 times q3, where q3 is a quotient, r3 is the new remainder. And the remainder must be greater than 0 and less than the divisor. Okay? And once we have r3 less than r2, we divide r2 by r3. That means that we're going to have r3 we're going to have r2 equal r3. The new quotient is q4 plus the new remainder, which is r4. And the remainder must be greater than 0 and less than the divisor. So it must be less than r3. Okay. Now, and we move on to this one here, and so on is going to be the next to the last sentence, which is which is r n minus 2 equal r n minus 1 q n minus 2 plus rn. For this one, we divide rn minus 2 by rn minus 1, and the quotient becomes rn minus 2 plus rn. And the remainder is rn, which is greater than 0 and less than the divisor. Okay, so once we have this equation, and rn is the last remainder, so if you divide rn minus 1 by rn, so we're gonna have rn minus 1 equal rn times qn minus 1. So the last equation, so that we don't have the remainder. Okay, so once the remainder is 0, we are going to have the greatest common divisor of A and B. So the greatest common divisor of A and B, according to Euclidean algorithm, is going to be Rn. So we start by divide B by A, and we have the remainder, and we use remainder to divide the divisor, and use the new remainder to divide the divisor, and all the way and so on to the last one that has the remainder of 0. Once you have the remainder of 0, you're gonna have the divisor that that divide the previous divisor, which is the greatest common divisor of A and B. So it is somewhere here. Okay. Now let's prove this theorem. Let's prove this Euclidean algorithm. For this one, let me remind you this theorem, which is this one right here. Yeah. So if you have A, B, Q, and R being integers such that A greater than 0, and if you divide B by A, it turns into be B equal AQ plus R, where R is greater than or equal to 0, less than A. So we gotta have the greatest common divisor of A and B equal the greatest common divisor of A and R. Okay, now let's use this theorem and prove this Euclidean algorithm. So we gotta let A and B be integers such that A is greater than 0. That means that we are going to divide B by A. And we are going to divide into two cases. The first case is the case where A divide B and A not divide B. Let's go to the first case. This case is the case where A divide B. Okay? The case where A divide B. So what is this case? So what happened when A divide B? When A divide B, we're gonna have division algorithm. Okay? So division algorithm. What does it imply? It implies that there exists integers Q and R such that B equal AQ plus R. But R must be 0. The remainder must be 0 in order to have A divide B. So by this theorem, what do we have? We gotta have the greatest common divisor of A and B equal the greatest common divisor of divisor and the remainder. So we gotta have theorem 2.4.8 implies that. What does it imply? It implies that the greatest common divisor of A and B equal the greatest common divisor of A and R equal the greatest common divisor of A 0, right? Because the remainder is 0. And the greatest common divisor of A and 0 is A. Okay? It's just A. Alright? And then let's go to the next case. The case where A does not divide B. So what happened to this case? What happened? When A does not divide B, what do we have? Again, when A does not divide B, division algorithm implies that. Okay, algorithm. What does it imply? It implies that there exists Q1 R1, there exists integers Q1 R1 such that B equal to A Q1 plus R1, where R is just greater than 0, less than A, which is the divisor. R must be greater than 0. If R is 0, this means that we're gonna have A divide B. But this case, A doesn't divide B, so R1 cannot be 0. So by theorem 2.4.8, what do we have? So we're gonna have the greatest common divisor of A and B equal the greatest common divisor of A, R1. Okay, this is what we have right now. And then what next? What can we do next? How do we have another divisor? Another divisor and another remainder. We have R1 less than A. So the next thing I'm going to do, we divide A by R1. Okay? But let's talk about this inequality first. So since you know that A is integer and A is greater than 0 and R1 is greater than 0 less than A. Okay? Greater than 0 less than A. So what do we have right here? You have this inequality, R1 greater than 0 less than A. So there are finite integers, positive integers. They are finite positive integers less than A. Okay, what does it mean by this? So let me give you some numbers. If you have R greater than 0 less than 10, what does it mean by this? So there will be, how many numbers are there? Greater than 0 less than 10. How many positive integers? 9, right? R1 can be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay? But in this case, R1 is just less than A greater than 0. So there must be finite number of integers greater than 0 less than A. Let's say it's maybe n minus 1 numbers. Okay? I want to choose n minus 1 numbers. Right? Let me think. N minus n numbers ranging from R2, R3, all the way to Rn minus 1 and Rn. Okay? I want to start with R2 because we have R1 right here. Now let's continue. So, since we have this inequality, so we gotta have integers R1, R2, R3, R2, R3, R4, all the way to Rn. So we gotta have Q2, R2, okay? Q3, R3, right? Q4, R4, and all the way and so on to Qn minus 1, all the way and so on to Rn minus 1, okay? And Qn must be with Rn, and these are integers. It's like we have the quotient of 2 with the remainder of R2 when we divide R1, when we divide A by R1. Alright, so what do we have right here? From this inequality, we gotta have A equal to R1, right? So we divide A by R1, so we can have A equal to R1 Q2 plus R2, where R2 is the remainder, greater than 0, less than R1. Okay? Like this, right? Now R2 is less than R1. So we divide R1 by R2. You're gonna have this equation R1 equal R2 Q3 plus R3. R3 is now the remainder. Okay? So what do we have next? The next thing we're going to do is to divide R2 by R3 because R3 is less than R2. So we're gonna have R2 equal R3 Q4 plus R4. So we're gonna have R4 less than R3. All right, and all the way and so on to Qn minus 1. Okay, and Rn minus 1. So what happened to this one right here? It must be Rn minus 3. So let's start with Rn minus 3 equal Rn minus 2 Qn minus 1 plus Rn minus 1. And Rn minus 1 is greater than 0, less than Rn minus 2. Okay? And Rn minus 1 divide Rn minus 2, right? So we're going to have Rn minus 2 equal Rn minus 1 and Qn and plus Rn. And Rn, let's suppose that Rn is the last divisor of Rn minus 2, but it is divided by Rn minus 1. So we have Rn greater than 0, less than Rn minus 1. So since Rn is the last one, let's say Rn is 1. Okay? And what is the number that is less than 1? Is 0, right? Is 0. Okay? So the last one is going to be, if you divide Rn minus 1 by Rn, so we gotta have Rn minus 1 equal Rn Qn plus 1. That's it. Okay? That's it. And what can we do next? How can we show that this Rn is the greatest divisor of A and B? So we use this theorem again. Okay? So now, we have the greatest common divisor of A and B equal the greatest common divisor of A and Rn. Rn is the remainder of B when B is divided by A. So what does this equation tell you? According to Theorem 2.4.8, when you divide when you divide A by R1, we gotta have the greatest common divisor of R1 and its remainder R2. Next one, you divide R1 by R2, we gotta have R1 R2 equal the greatest common divisor of R2 R3, right? Because R3 is the remainder. And this one right here, we're gonna have the greatest common divisor of R2 R3. So we divide the greatest common divisor, we divide R2 by R3. That means that we're gonna have R3 and and the remainder, which is R4. Okay? Now let's go to the next one here. Let's go to here. Now, what can we do next? So from this equation here, we gotta have the greatest common divisor of. So if you take a look at the pattern, we gotta have Rn minus 3, Rn minus 2. Okay? Because we what do we have? Because we have the pattern right here, and according to the previous equation, we divide this number right here by Rn minus 3, right? And the common divisor, and the remainder right here is Rn minus 2. Okay? And now from this equation, we have Rn minus 1 less than Rn minus 2. So we gotta have Rn minus 2, which is the divisor, and the remainder Rn minus 1. And next one right here, we gotta have Rn minus 2, Rn minus 1, which is the greatest common divisor of Rn minus 1 and the remainder n. Okay, and then what about the last one here? Okay, let me write plus 0 right here. In this equation, we divide Rn minus 1 by Rn, and the remainder becomes 0 right here. So we gotta have the greatest common divisor of Rn minus 1, Rn, becomes Rn 0, and it turns out to be Rn. Okay, great. So what do we have right here? So by theorem 2.4.8, we gotta have the greatest common divisor of A and B equal A R1, and A R1 is R1 R2. R1 R2 equal to this one here, R2 R3. Okay, R2 R3 equal to the greatest common divisor R3 R4. Okay, and all the way and so on to the greatest common divisor of Rn minus 3, Rn minus 2 equal to the greatest common divisor Rn minus 2, Rn minus 1 equal to the greatest common divisor of I minus 1 and Rn. Okay, and it turns out to be the greatest common divisor of Rn and 0, which is the greatest common divisor of Rn. So this number right here is now the greatest common divisor of A and B. Okay, so we have the proof of Euclidean algorithm already. If you want to find the greatest common divisor of A and B, you start with divide one of these numbers, okay, and try to divide so that you have, so once you have the new remainder, use the new remainder, divide the divisor. Okay, and once you divide the divisor, you're gonna have the new remainder, and use the new remainder, divide the previous remainder. Okay, and try to do something like this all the way and so on, so that the remainder becomes 0 right here. Okay, so the latest divisor becomes the greatest common divisor of A and B. And that's it for this